because that'll be fun. All right. So the first thing I actually want to show you, because I already have it up. So here are the scores of all 4 cohorts. The only one that y'all got wrong, by the way, congratulations, first of all, you got 7 out of 8 of them correct. The one you got wrong was number 13. That one had, I think it was a piecewise function, and you had to try to determine what the left-hand limit was. 3 of the 4 cohorts got that one wrong, and they either picked the 2 incorrect answers they picked were either the right-hand limit or that the limit did not exist when we were looking at the left-hand limit. So I think that's what y'all did. I think you picked the left-hand limit. I don't remember off the top of my head which it was. I can go look. But again, all the 3 cohorts who didn't get that one correct picked either the left-hand limit or the right-hand limit value or said that the limit didn't exist, which were both things, but we were looking for what the value of the left-hand limit was. So if you want to go spend some time and go back through that progress chart, now that you know I can get for sure 8 of them correct because we talked to them through and worked them out, worked through the others, and I'll open up the scoring on that so that after you complete it, you can look and see what did you get correct, what didn't you get correct, and kind of just double check to see how you're doing on those. Alrighty. If you don't want to, that's again also your prerogative. I would recommend that you spend the time to do that just to kind of keep reinforcing those things as we keep moving along. All right. Speaking of moving along, we are... Okay. You had some weird things coming out my way. So we're going to keep moving along. We're going to move on to the chain rule. The chain rule is another rule that we're going to need because we talked about rules for finding derivatives of functions when there's 2 or more functions multiplied together, and like how to find that derivative, and how to find the derivative when there's a ratio of 2 functions, a fraction of 2 functions, however you want to call it, a ratio of 2 functions in particular, a quotient. Find the derivative of that. But what if there's a function inside of another function? How do we handle that? That's what we're going to focus on today. So that's what the chain rule is all about. And composed functions are like onions. They have layers. We're going to be successful when we can find the derivative of a composite function. I really should update these learning objectives because, man, I really wasn't that creative when I came up with these ones. RIP. All right. I want you to take a hot second. And by hot second, I mean a cool 30 seconds. I want you to attempt to find the derivative of each of those. Whatever you think it is, try. See what you get. Go. Just on your paper, sketch out what you think it is. The most important thing isn't that you get them correct. The most important thing is that you wrote something down to try. All right. Here's what I got. If you go look up the rule, what's the derivative of e to the x? Someone can either unmute and tell me or type it in public chat. What's the derivative of e to the x? It's a fabulous guess, Tyler, but it's just e to the x. It's a tricky one because that would be true if we were saying what's the derivative of x to the e. You would subtract 1 and multiply by that. But the derivative of e to the x is just e to the x, which is why it's super freaking sweet. And it's like my favorite function because of this, that it's its own derivative. It's so freaking cool. So here we go. Is that it? Does it seem like it's just because this part shouldn't change. It should always be e to the x, e to the 3x, e to the x squared. Is there anything that's bugging you about what's on the slide right now? Half of the parentheses. It feels like something's left out. Half of the parentheses. We see half of the parentheses, but where's the right parenthesis? We see left. Where's the right? There's something. Holy crap. There's more to G prime and H prime than there was to F prime. Where the hell did those numbers come from? Like, I know for sure, for a fact, that F and F prime are all these are 100% correct. But based on our rules, I know that the derivative of e to the x is e to the x. I know that for a fact. But in order to get the correct derivative for G and H, there's an extra 3 that's the whole thing's multiplied by. And there's an extra 2x that the whole thing's multiplied by. There must have been an operation, that the same operation that somehow happened in G and H, or G prime and H prime, to get those things. Like, we can't, like, if we're finding the derivative, we did an operation, like the same operation, we just found the derivative, and then the 3 and the 2x appeared. It is a question, why? Like, where did the 3 and the 2x come from? So here's the thing I'm thinking about. I'm wondering what connection they came from the exponents. It sure looks that way, right? 3x and 3, x squared and 2x. How do I get 3 from 3x and 2x from x squared? Flip them. Kind of. What do you mean by flip them? I appreciate the bravery in answering, Greta. And Lizzie said the derivative of just the exponents? Yes. Because these are g of x and h of x technically are composed functions. There's another function inside of the function. And that changes how it grows and the rates of growth. And how? Like this. 3 is the derivative of 3x. 2x is the derivative of x squared. Why don't you try finding the derivative of these 3 real quick? I'll give you a minute. Go. Oh, while you're doing that, I was going to try something. Bam. All right. Let's see. Derivative of sine is cosine. Derivative of sine of 3x is cosine of 3x times 3. Derivative of sine of x squared is cosine of x squared times 2x. That seems to be continually to be going. The question is, why does it have to be that way? Like, what governs that? Why must that be a thing? Like, The pattern works. It exists. But why? But why? Because you were doing pretty good with differentiating functions. But now we have f of g of x. What about f of g of h of x? Can we handle those? Are those just going to completely destroy us? No. Because composed functions are like onions. They have layers. We're not going to let them destroy us. Maybe a little bit of mauling, but not enough to like kill us or completely maim us. Just enough mauling to learn from it. So because they have layers, we can look at it that way. And we're going to find out the derivative using the chain rule. And the chain rule is coming to bat for us. Here's the chain rule. When you want to find the derivative, d over dx, of a composed function, f of g of x in this case, you get f prime of g of x times g prime of x. Ooh, I thought of something we could add. I'm going to add something to this while we're talking about it, which will help make sense to what we're going to do. Oh, come on. Just be a person. Be a thing. Be a thing. Okay. Be an a-hole. That's fine. Oh, hey, look at that. We're going to add animation. Yeah, fade in. Boop, boop. We're just going to, this bad boy's going to come up. So here's two different ways you can state the chain rule. The reason I added the second one is because that's the kind of the version that I subscribe to a lot. I like to think about the inner functions and identifying inner functions and going from there. The other reason I'm trying to point that out is the other day I mentioned, hey, go fill out that derivative table from the front of the book. And you're like, what the hell, Lass? Like, I don't understand what the hell's going on. All the rules in the front of the book are described using chain rule, where u is some function of x. I don't know what it is. We have to define u in order to use u. That's how u substitution works. If you remember from pre-calc chapter 3 last year. And if you don't, that's okay. We're going to do a little bit of it now. So to help supply the chain rule, it can be helpful to look for the innermost function or the innermost layer. To find the innermost layer, so we want to find the innermost thing. To help find the innermost layer, think about what is the, if I plug the number in for x, what's the first set of operations I'm going to do? That is going to tell me what my innermost function is. So like for this first one, my innermost function, what might be my u, is x plus 1. Because the very first thing I do when I plug in, like say 7, is I'm going to add 1 to it. So x plus 1 is my innermost function. Sine of 2x, my innermost function, is 2x. For this square root of all of this stuff, that stuff is my innermost function. Because there's a couple other things I do before I get onto another grouping symbol. Okay? Tangent squared of x. I'm going to pose it to you. Is the squared or the tangent the innermost function? Take a guess. Be brave. Take a guess. Tangent is the innermost function. So thank you both, Emma and Evelyn, for taking guesses and being brave. I appreciate that. It's tangent because when we do tangent squared of x, we don't write it this way because it's just a ridiculous amount of parentheses, but it'd be tangent squared. because tangent squared really just means tangent times tangent. So it'd be tangent squared. Now, each of these can be rewritten so they look like our rule, like the basic rules that we have. I don't want to say they're easy rules, they're basic, as in we use the basic rules to apply to different things. So like this first function, all of a sudden looks like that, which can be rewritten as u to the negative first. And then you can use power rule and go from there. The second one is just sine of u. Again, that's a basic one that we can work with. Square root of u can be rewritten as u to the 1/2. We use power rule and go from there. U squared, power rule, go from there. So the chain rule helps us rewrite stuff so that we can go from there. Again, we can find the derivative of these, I should say, instead of easily, more easily, because these look like the rules that we've been using, okay? So let's look, I have p of x and f of x. I want to show you how I approach it using u substitution. The more and more familiar you get with chain rule, the less likely you use the actual substitution. You'll just identify what the inner layer is and just multiply. If you want, you can start working that way. That's totally fine. I'm going to show you using u substitution because I think it's easier, even though it takes more time to get that first. And then as soon as you get that and start seeing the nuance of it, then you can kind of skip using the substitution. Also, I'm using it to front load for later on when we use u substitution going the other way. So for p of x, my innermost function is this bad boy, the 3x minus 2x squared. So I'm going to let u equal this innermost function. Again, I know it's the innermost thing because when I put in a value for x, it like if I want to evaluate like p of 7, it would do 3 times x, or 3 times 7 minus 2 times 7 squared. So that's my innermost function because it's the first thing that would happen if I plugged in a number. So I'm going to let u equal that whole thing. And by the way, if you saw that and you're like, I would do the exponent first, and you said, well, let u be negative 2x squared, and you put that back in there, it wouldn't necessarily make it easier for you. It would just look different and still kind of hard. So when you're picking u's, pick a u, that innermost function that's going to make it look simpler to work with. So in this case, if we let u be this, then p of u is u to the third. U to the third is one of our more basic rules and ones that you've worked out by hand, both in pre-calc and in 2.1. Well, p prime of u is going to be u 3u squared times u prime. Because again, I said use some function of x. Like I can't take a derivative of a composed function without remembering to find the derivative of the inner piece, which is what I need to do here. So u to the third, the derivative of this with respect to x, saying it's a function of x, I get 3 times u squared, 3u squared times u prime. At this point, I'm done. Like that's the derivative. But I want to put it back in terms of x because that's the notation that I'm working with. So p prime of x, I just substitute u back in, and then u prime, well, u is 3x minus 2x squared, so u prime is going to be 3 minus 4x. And you can see that right here. Boom, 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 boom. So we were using that idea of that u and u prime all the way back at that first example. If you re-looked at e to the 3x as e to the u, where you let u equal 3x, then the derivative would be e to the u times u prime. In fact, it still works for e to the x too. If you do e to the u, let u equal x, derivative of x is just 1. So really, f prime of x is e to the x times 1. But we don't ever write times 1 because why? But over here with these two, u prime is something of substance. So we actually include it and want to talk about it. For f of x, we already let the cat out of the bag in the previous one, and I forgot to hide the let u equal sine of x. So that's a rip on my behalf, but whatever, it's still all we need. Again, re-emphasizing that sine of sine squared of x. The inner function here is sine. Again, that's a tricky thing that you're going to forget at least once, and that's okay. Or you're going to forget it once, get something really goofed up, recognize your mistake, and probably won't make the mistake again. But if I let u be sine of x, all of a sudden sine squared of x becomes u squared. U squared is basic to find the derivative of. F prime of u is 2u times u prime. I know what u is. It's sine of x. U prime is cosine of x. So I just plug them in. So I want to point out some numerical evidence, and that this isn't just me saying, hey, this is the way it is. I'm going to go to trusty old Desmos, because I think a lot of us trust in Desmos a lot for things. So I said, let f of x be e to the 2x, and let g of x be the derivative of f of x. I found out g of 2 was 109 something. G, or e to the 2 times 2, if I plugged in 2 for f of x, I would get 54 point this. That looked like it was about half as big as it should be. So I multiplied by 2, and I got what I needed. And if we actually numerically or like algebraically figured out the derivative, what g of x should be, it should be e to the 2x times 2. E is the number e. So 2.71828, 1828, and then something else after that. Yeah, it's just that Euler's constant is technically what it's called, but it's that constant like pi, like e and pi are like the transcendental numbers that we use like all the time. So thank you for that question. That's an important thing to keep asking. So you can see that it works for this one. I was like, well, what about e to the x squared? So f of x is e to the x squared. G of x is the derivative of it. Well, g of 2 was 218. E to the 2 times 2 was 54. I really needed that 4 times bigger to see what was happening. But that by itself didn't really help me. So what I did is I went and made a table of g of x, e to the x squared, and 2 times x to the e x squared. Remember, g of x is the derivative of f. So this green column is the derivative of f. This purple column is f. This is what I think the derivative of f is. If you look at the green and the black columns, the numbers are the same. What I'm trying to point out here is that if you don't, I'm showing you some numerical values to show you that it isn't just something I'm saying that I'm doing to you, that I'm making you remember the chain rule and like, oh crap, this is a lot of garbage and Lass is throwing at me. I'm trying to show you that when you numerically do the things, that's how it works out. If you don't believe these static shots, I can make a little GIF later and put that in here to show you how that works. But basically, again, the whole point of this slide is to show you numerical evidence that chain rule needs to be applied. Otherwise, you're missing information. So it's nice to have numerical information sometimes. And this is supporting evidence. This itself isn't a proof. This is just supporting evidence that this is a thing. Okay. And again, if you just type these things right into Desmos, they'll start doing this stuff for you. I'd highly recommend that if you're struggling with stuff and trying to figure things out, or you want to check your derivative answers, type in f of x, type in g of x like that, then say, what's g of 2? Or whatever value you want. That'll help you out. All right, Greta, I'm going to come back to you in a hot sec. So yes, that's it for today. My plan is to spend 2 days on this. So my plan for next time is to do a little more of the numerical playing around and checking, and I just have to figure out how I'm going to write that all out. I'm going to go sketch in my notebook later and try to figure it out. But here's your practice. It's due soon. I don't know, whenever you get it done. But that's what I have for you today, folks. So as you have questions on the practice, remember, post a question or two in the AB channel in Discord, because your questions will help everybody, not just you. Most of the time when you send me a direct message, I'm just going to reply. If I think it's particularly valuable and not something that's embarrassing in any way, I'm going to ask you to repost it in the public chat, because I think there's some value to that. Okay. And it's nice to see more people using that as a resource. Yeah. I think that's what I have for you right now. So on that note, have a wonderful day, folks.